Welcome to the University of Kentucky's Center for Applied Artificial Intelligence. Visit us online at caai.ai.uky.edu to learn more.
On behalf of the Appalachian Trail team, I wanted to thank the organizers for the opportunity to share our thoughts and work. From Southern Appalachia in Georgia to Northern Appalachia in West Virginia, our collaboration has grown through visiting scholars from Carabrook University in Turkey to institutional collaborations with the University of Louisville and the establishment of the Kentucky Pathology Data Trust. As with many of you, we believe the development of foundational models that can self-supervise through domain-specific methods are the next evolution of model development. It's also important that we work together not just to develop techniques, but to establish diverse data representations from across the globe. As foundational models are able to understand complex domain patterns, generative AI can replay these understandings to advance scientific discovery and clinical care. In addition to model development, our work focuses on leveraging parameter-efficient fine-tuning and model layer replacement at time of execution, allowing for strong generalized foundational models to be adapted to many downstream tasks efficiently and for operational purposes within a common ecosystem. We thank you once again for the opportunity to share our work and look forward to future collaborations.
Our team's first priority was to understand and structure the large unlabeled competition data set by using existing pathology foundational models. To ensure we are feeding our model with high-quality data as we scale, we are moving away from simple k-means to a consensus clustering approach. We hypothesized that if an image falls into the same cluster across Unitu, Conch, and Ficon, it's more likely to represent a pathological concept rather than noise. We will use statistical methods and inspection from our team's pathologist, Dr. Gondam, to verify this. Then we can construct a seed data set from the pseudo-labels constructed by our approach to begin the training of our model. This seed data set serves two purposes. It can serve as a test data set to evaluate our model via linear probe, and it can directly be used to train our model via contrastive loss, where the model will learn to push images in the same class towards each other in the embedding space and to push dissimilar images apart. We plan to use this learning objective as an initial warm-up phase, giving the model a baseline understanding of the data before introducing other self-supervised learning objectives. This image shows the UMAP visualization of the clusters we generated in our preliminary experiments with Unitu embeddings. After creating our baseline model, we will utilize a DynoV2 style self-supervised learning architecture. This relies on a multi-view student-teacher framework where both networks are vision transformers. We leverage this design to enforce multi-scale learning, generating hierarchical representations across 20 times and 40 times magnifications. The student model is fed local crops representing the higher magnification details constructed using standard pathology-specific augmentations. The teacher, conversely, sees global crops, which are high-level, less augmented versions of the original image. The student is trained to predict the same embedding representation as the teacher, while the teacher is updated as an exponential moving average of the student's weights. To optimize training stability, we have integrated Optuna with Weight Watcher. Optuna acts as our automated hyperparameter optimization framework, searching for ideal configurations for parameters like global learning rates. Complementing this, Weight Watcher provides a principled method for health monitoring. By analyzing the spectral density of the weight matrices, it enables an adaptive learning rate policy that adjusts the learning rate for each specific layer based on its training state. This prevents overtraining within specific layers, and it accelerates the model's overall convergence. Foundational models are best trained on diverse, balanced datasets. Typically, balancing involves trimming the dataset to remove overrepresented labels. However, we aim to utilize the full dataset by implementing a novel balancing approach. We employ a multi-expert distillation training strategy to handle any imbalances we discover. In this strategy, the model parameters are distributed across GPUs using FSDP, or fully sharded data parallel. Each cluster in the dataset is then assigned to a separate GPU, allowing an expert model to be trained specifically for that cluster. Finally, these expert models are distilled into a single unified model representing the ensemble averaged knowledge of all the experts. This approach mitigates bias towards overrepresented clusters and ensures that each expert model is trained for an equal number of steps on its assigned data, promoting balanced generalization.
A powerful advantage of training a foundational image model is that it becomes a shared backbone for a wide range of downstream tasks. Using modern parameter-efficient fine-tuning frameworks, such as PEFD and LoRa, which stands for low-rank adaptation, we can attach lightweight adapters to the foundational model without retraining or modifying its core weights. These LoRa adapters can be swapped in dynamically to specialize the foundational model for tasks like tumor classification, cell type detection, or even pixel-level segmentation, all while keeping the same base model frozen. This design makes the pipeline both scalable and efficient. Because the only unique components for each task are small adapter layers or lightweight heads, GPU memory requirements remain low. You avoid the overhead of hosting multiple large models and instead maintain a single foundational checkpoint, adding adapters only when needed. In clinical environments where hardware may be limited but the diversity of tasks is high, this approach offers a practical path to deploying AI systems that remain versatile, updatable, and resource efficient. With our data curation and training strategy in place, our immediate next step is applying this full pipeline to the complete competition dataset. We are confident this approach will yield a robust, clinically useful foundational model. Thank you.